Okay, here I'm just going to do a couple of example problems that should help you with the assigned problems. So in the first one, let's say that we have a disk that's connected to the wall by a pin. This is sort of like a pizza cutter looking thing. So this arm is connected to the center of the disk and connected to the wall. And at this instant, the disk has an angular velocity of 10 radians per second, positive, so that's counterclockwise. And we'll say that this point here has a force applied to it of 20 newtons. This disk will say has a radius of 0.3 meters and a mass of 0.5 kilograms. And let's calculate what the acceleration is of this point on the disk. So I'll call this A, and we want to calculate the acceleration vector of that point A. Okay, so the hinge is going to be the center. And we're going to use rotational Newton's second law to calculate the angular acceleration. And then from that point on, it's just like the rotational kinematics problems you did. It's very much like circular motion. So I'm going to start with a free body diagram. And there are a few things going on at the middle. There's the weight of the disk. That always acts at the center of the object. So that's 0.5 times 9.8. So that's 4.9. And then there are the unknown forces that are applied by the hinge. I'll call those Rx and Ry. And then there's the force down here at the bottom of 20 newtons. And those are all the forces acting. The moment of inertia, we're doing this calculation about the center because that's where the hinge is. So this is going to be 1/2 times the mass times the radius squared. And that gives 0.0225 kilogram meters squared. So that's the moment of inertia. And now we have to calculate the moments produced by all these forces. There's 3 forces here. The moment produced, or the torque produced by these forces Rx and Ry, well, both of them act at the hinge. And so the distance is 0, and so the moment has to be 0. The weight force, this one often produces a moment, but since in this case it's acting, the line of action of this weight force goes right through where the hinge is. D is 0 for this too. That distance is 0, so the moment is 0. And then the last one we have is this 20 Newton force. That's plus or minus. That force is already perpendicular to the line from the hinge to where the force is applied. And so the distance for this 20 Newton force is this. And that's just the radius of the disk, which is 0.3 meters. So we have a force of 20, a distance of 0.3. with the hinge at the center, a force here in this direction will make it rotate clockwise. So we're going to take the negative, and this gives us negative 6.0 Newton meters. And so the net moment, the net torque, is the sum of these three things, and so that's equal to negative 6 Newton meters. And now we have everything we need to put this into rotational Newton's second law. The net torque is equal to the moment of inertia times the angular acceleration. And so the angular acceleration is negative 266.6 repeating, and that's in radians per second squared. Okay, so now we figured out the angular acceleration. Now what we need to do is figure out, do the circular motion calculation for that point A. Okay, so we know that the angular velocity, that was given that it's counterclockwise at 10 radians per second. We calculated that the angular acceleration is clockwise, so it's this direction. So at this point that we're asked about, the velocity vector is this way. The angular acceleration vector is the opposite way. The angular acceleration vector, the angular acceleration is the way that I drew it here. What I drew here in the green vector is the tangential acceleration. And then the centripetal acceleration is towards the center. And we have all the values that we need to calculate these. So let's just start going through them. All we're looking for is the total acceleration. There's no need to calculate that velocity vector. It wasn't asked for. So I'll just go right into that. The centripetal acceleration magnitude is omega squared times r. So that's 10 squared times 0.3. So that is 30 meters per second squared. And that's in the negative I direction. So negative 30 meters per second squared times I. And now we'll go to the tangential acceleration. The magnitude is the absolute value of alpha times r. So that's 266.6 repeating times 0.3, and that is 80 meters per second squared. You can see from the drawing we figured out that the tangential acceleration is in the negative j direction. So that's negative 80 meters per second squared times j. Now the total acceleration is the sum of those two parts. So the total acceleration of that point A is negative 30 meters per second squared times I minus 80 meters per second squared times j. Let's do one with a rectangular beam. So let's say for the second example, we have a rectangular beam like this. Let's say the length is 1 meter. And let's say in this case, we're not even given a thickness. So we're just going to assume that this thickness is small compared to the length. And we're just going to treat it like 0. It turns out that that gives you a pretty good approximation a lot of the time because of the fact that you're squaring these dimensions in the formulas. And we'll say that the mass of this beam is 5 kilograms. And at this instant, let's say that this beam is moving, let's say it's sort of falling down, which would mean that the angular velocity, it's counterclockwise, so this is going to be positive. So let's make this 4 radians per second. And we want to calculate the acceleration of this point A at the end. And we're going to assume, well, I guess we did in this one too. I'm going to assume that the downward direction is toward the bottom of the page, so we're going to have to put gravity in this problem. Okay, so the first thing we're going to do, again, is use rotational Newton's second law to calculate the angular acceleration. And so I'll start with a free body diagram. Over here, we have our 2 unknown forces. Those are applied to the beam by the hinge. And then in the middle, we have the weight force, and that is 5 kilograms times 9.8, so 49.0. Now we have to calculate the moment of inertia for this rectangle. This is equal to 1/3 times 5 times the length squared plus 1/12 times 5 times 0 squared. So you can see this term just goes away. And we're left with 1.6 repeating kilogram meters squared. And now we have to calculate the moments applied to this body by the forces. So the moment or the torque applied by those forces R is 0, like it always is. The moment applied by this 49 Newton force, I guess I'll call it mg, is plus or minus 49 times the distance from the hinge to where the force is applied. We didn't have to move the force at all along its line of action in this case because that force is already perpendicular to that red line. The length of that red line, d, is half of the length of the beam, so just 0.5. And now you have to think this force with the hinge over here at the right, would this weight force make this body rotate clockwise or counterclockwise around that hinge? This force would make it rotate counterclockwise, so we want the positive. And so the moment produced by the weight force is 24 And this is Newton meters. Add these up and you get that the net torque is 0 plus 24.5, so just 24.5. Now we can put these into rotational Newton's second law. Which says 24.50 is equal to 1.6 repeating times alpha. So alpha is equal to 14.70, and this is radians per second squared. Now that we have the angular acceleration, all we have to do is the circular motion part. So if this is the beam and the rotation is about this point here, then the circle of the path is going to look like that. Okay. The angular velocity and angular acceleration are both counterclockwise in this case. So omega and alpha are both this way. And that means that the velocity is this. And the tangential acceleration is in the same direction. And then the centripetal acceleration is always towards the center. And now we just have to calculate the two parts of that acceleration. The magnitude of the centripetal acceleration is omega squared times r. Omega was 4. So this is 4 squared times the radius of this circle is the length of this beam, so 1. And we get a centripetal acceleration magnitude of 16 meters per second squared. That's in the positive I direction. And so this is 16 meters per second squared I. And then the tangential acceleration magnitude is the absolute value of the angular acceleration times r. So that is the 14.70 that we just calculated times the radius of this circular path, 1. And so this is 14.70 meters per second squared. It's in the negative j direction. And so we get negative 14.70 meters per second squared j. Add those two parts together, and the total acceleration is 16 meters per second squared I minus 14.70 meters per second squared j.